Now let's move on to section 4 and section 5 of this notebook. We already dealt with area and volumes in chapter 6, and we're doing it for parametric curves, but essentially they are the same. All you have to remember is the chain rule. Now, integral of y times dx is exactly the same formula that we use for area computation in chapter 6. Y is f of x, then we have f of x dx. But then again, by chain rule, this dx is dx dt times dt. And eventually, we end up with a t integral, and that is for parametric curve. If we do x dy, where we have x equals to g of y, kind of like that, well, we can generalize it to parametric curve. Then dy is same as dy dt times dt, again by chain rule. So we have this kind of formula. And, well, because the original formula that we used in chapter 6 are being reproduced here and just coupled with a chain rule, I don't think anybody should have any kind of trouble getting through with these formulae. Let's do one problem. Let's see. How about problem B here? And if I remember correctly, it'll generate an interesting picture right over here. Yes, indeed. So we have this kind of curve, and this is a moving particle model, and we want to find out the area inside this clover. So how do we do that? Well, we can calculate using Mathematica integral of y times dx, y times x prime of dt, that's dx, or x times dy, x times y prime dt. Calculate those two. One is 2 pi, there's negative 2 pi. You don't have to worry too much about it. Area always has to be positive, so flip this negative to positive 2 pi and that's it. So if you want to do the symbolic computation, yes, you can do it like this. Y dx, dx is equal to x prime times dt. So putting everything into the same formula that we use in chapter 6 and apply chain rule, this y part is, well, in parametric equation like this, and then dx is x prime dt. After computation is right over here. So some simplification with this foiling, and we have this kind of integrand, and all you have to do is calculate this integral over there. But then again, calculating this integral is very, very tedious thing to do. We have to use power reduction formula for sine squared, again power reduction formula for this cosine squared, and then sine times cosine, so you can change those into sum of two trigonometric functions, sine plus sine, kind of like this. And then, well, calculate the antiderivatives, and then this is what we get. We have all this cosine of 2t, sine of 2t, and so on. Those are all periodic. So plugging in 2 pi, plugging in 0, they're going to cancel out all, and you're going to get just this part, and then you end up with 2 pi. How about this problem here, this method, x dy? Well, x is this part, and then dy is y prime dt. Here it is. After computation, we get something like that. Very similar to the previous problem, actually. Is it the same? I think it is the same, except for the sign. And then we end up with negative 2 pi, but don't worry about that. All you have to do is flip it over to positive. That has something to do with the direction of the motion, as a matter of fact. Let's see, do we have enough time? Let's do a cycloid problem. Calculate the area underneath one arch of a cycloid here. So t equals to 0, and then all the way out to 2 pi. So that part, if you use x dy, then, well, you can see that as t goes gets big, x is increasing, so this can work well with y dx integration, solution 1 in this case here. And then let's go ahead and do that. This is y and then dx, so x prime dt, and FOIL it, and then we have this kind of function there. Calculating this integral using the power reduction formula in the end, we have 3 pi r squared, and that wasn't too difficult. Compared with the previous problem, this was not much of a big deal. If you use x dy, you're gonna get a little bit different computation, but you end up with negative 3 pi r squared, but area has to be positive. You can always flip over. So this is x dy, x, and then dy. So calculating, we have t sine of t, so looks like you'll have to use integration by part over there. Otherwise, pretty much the same. Let's see, let's do a volume problem this time. What is the volume formula? Washer method, pi y squared dx, the same formula we had been using all the time, but dx is same as dx dt times dt. That's coming from the chain rule, of course. Same thing goes to y. And how about shell method? 2 pi xy dx, and then this dx will be replaced by dx dt times dt. So both way it works great. Washer method with respect to x-axis, y-axis. Shell method respect to x-axis, y-axis, or y-axis, x-axis, respectively. And everything is changed into dt. And technically it may be a bit of a difficult computation afterwards, but in terms of theory, not much is there. For example, here's an example of a solid of revolution given by a cycloid. I think it's here. One arch of cycloid, and rotated, we end up with this kind of football. And how to find out the volume of that? Washer method. Let's go with washer method. Pi y squared dx, this one. So pi y squared, this one squared, and then dx, so it's x prime dt. So after simplification, we get this integrand. You'll have to use a lot of tricks that we learned in chapter 7 to get it done. This one is power of deduction, and this one cosine squared times cosine. We end up with 1 minus sine squared times cosine of t, and so on. We end up with this answer. If you use shell method, by the way, then that's gonna be this one right over here. The rotation has to be according to x-axis, so it should be dy. So it's gonna be something like that, and then dy is y prime dt, so y prime dt, kind of like that. And after simplification, we get this kind of integrand. Calculating that integral is pain in the rear end, but it is possible. It is all done here, and then I took really long time get this thing right. But then again, even though I did this one, I took a lot of time doing it, but I don't enjoy this much because I don't think this is particularly important. Most of the time we just use computer algebra system, Mathematica as a matter of fact. Alright, enough time to talk about section 5, Pappus theorem. Centroid of a certain region is defined like this. Here's a picture. Okay. We have a graph of a function y equals f of x and y equals g of x, and then the centroid of the region captured by those two are given by this formula over here. This is the x-coordinate of the centroid, this black point, and then y bar, like that. And then the derivation of this formula is given in the textbook, but I think it's a waste of time. I don't want to deal with those. It's just too narrow a topic. Then area, of course, you know the area. area captured by these two curves. F is upper function, G is lower function, so 1 over A should go over there to x bar and y bar. And the centroid for parametric curve makes a little bit more sense actually. And here's an example of parametric curve. Oh, we have something like that, and the centroid is down here in red dot. And let's see, area can be calculated by y integral of y dx, isn't it? And to this integral, if you simply multiply by y, to y dx, if you multiply by x, then you're gonna get centroid for x, and then multiply by another y, then you're gonna get y by, that does explain this 1/2 of y squared. Oh, never mind. So let's just regard those as a formula and that one as a formula, and just put those in and then do the integral computation, and you're gonna get the centroid. Now, how do you use centroid? Pappus theorem is the one. The area of the cross-section and the volume of the solid of revolution can be calculated by 2 pi r times a, where r is the radius of rotation of the centroid, and then a is the cross-sectional area. Here's an example. Let's see. Okay, we have this kind of strange region, and then rotate it with respect to which axis? Obviously, I rotate it with respect to x-axis. Yeah, kind of like that. Strange figure. And how do I find out the volume? This is kind of cut open to see the cross-section. Yeah, cross-section is there. How do I find out the volume? We can use rather stupid method, but you can use Pappus theorem, because the cross-sectional area is given by the integral, which is planar integral, so you can do that. And centroid right over here, so the radius of the rotation is just y-coordinate value, this one. So put those into this formula over here, and then you're gonna get the volume. Well, this used to be useful for early on when we didn't have computer, but with computer, computers can handle volume formula with those Washer methods just as well. So what's the point here? This is one of those rare examples that Pappus theorem can be used really well. And solid of a torus, solid torus given by rotating the circle around, which kind of looks like this one, kind of like a donut. What's the volume of that? Well, one way to do that is to use the Washer method, the top curve and then rotate it around, bottom curve rotate around, and use Washer method. It's gonna take you forever. But if you use Pappus theorem, it's not much of a big deal, because the centroid is clearly the center of this circle, which is, well, x minus 4 squared here, y minus 3 squared. So centroid is 4, 3. The radius of rotation is 3 because rotation is with respect to x-axis. And then the cross-sectional area is what? This is 2 squared, so pi r squared is pi times 2 squared, so 2 pi. So if you put everything into this formula over here, 2 pi times r, the radius is 3, times the cross-sectional area, 4 pi, so we're going to get this kind of volume computation, 24 pi squared. If you use Washer method, then the solution becomes rather long, and then if you use shell method, solution is almost equally as long. But then again, if you use Mathematica, either way you can answer quickly, so what's the point? Well, here you go. That's the conclusion.